Greetings, I am Stewin, and this is a modular copper bulb based 8-bit computer. It runs at 1.25 Hz with effectively three main registers. It has 33 bytes of main memory. It can store up to 156 5-bit instructions and its 4 banks of ROM. And it even has some room for adding more instructions. For example, expanding its addressable memory to something like 256 bytes. This is the second Minecraft computer I have built, and I think it is, at minimum, a very unique design. In my mind, converting real-life computers to Minecraft has been done plenty of times, and it has been done very effectively. However, Minecraft is not real life, and there are techniques that we can use in Minecraft that would be inefficient or expensive to do in real-life circuitry. That is why this computer is not designed like a real-life computer or using real-life assembly. This architecture is based off a very different programming paradigm. Most every circuit in this computer is unique and specific to this approach, and just for fun, I used as many copper bulbs as possible. Results of those experiments are mixed. On one hand, the main bus and instructions are very interesting. Data storage is very dense, and the computer is effectively pipelined by default. However, some of these copper bulb alternative circuits require very specific timings or very long, inefficient programs. The end result is a working computer, and I want to show off everything I built, good and bad, but standard models are standard for a reason, and a few of these circuits should absolutely be replaced with more standard alternatives in any future versions. The screen especially would be way better as a texture pack based or even just larger uh, redstone lamp type design. The first Minecraft computer I built is over here. It is also 8-bit, but it was limited to a set of 8 instructions called BF. Every operation ran on a single integer array with no arguments, and the entire list is as follows: plus, minus, shift to the next number in the array, shift to the previous number, input, output, and loop, start and end. This one also had no central clock. Each instruction had its own timing. Programs only reached up to 100 instructions long through this entire loop, and the limited operations they could do meant very long programs. The obvious shortcomings of this circuitry and this approach gave me many ideas for a new version. Since I had a lot of trouble fitting all the mathematical operations into this space, I wondered if I could have all the operations be separate circuits instead of going for one central ALU. I realized that with copper bulbs, what I can do is I can give every instruction its own copy of the main registers, and the main bus can signal toggles instead of actual values. Over here, we have a few tests of how to implement that idea, first horizontal and then vertical as I settled to. This central orange bus carries toggles for each bit of the main register. Underneath it, the 5 green lines pulse for each instruction, and the matching combination of copper bulbs will signal the instruction to output its value to the main line. Every other instruction receives the new value and will basically pre-calculate what it might need to output next. A few instructions require 2 inputs, so this second bus carries a separate register value for those. With 5-bit instructions, it can have up to 32 different operations. Currently, this computer uses 26 of them. For math, I have increment and decrement 1, bit shift up and down 1, zeroing, random numbers, and inverting. Using the second integer, I also have AND gates, XOR gates, as well as saving, loading, and swapping between the two, and an extra swap to a third backup register. The screen is set up as an 8x8 grid where each pixel can be in 4 states: full off, half left and right, and full on. Printing to it is done with 2 masks, one operation to choose from the 8 rows, and another to cycle pixels through their states by column. It can be reset to empty with a button or instruction, though that function is what makes it so deep and laggy. The resulting screen is good enough for displaying multiple games, such as tic-tac-toe or Connect 4, or theoretically checkers, not chess. But a more standard addressable design would be larger and faster and easier to program. Input is under that. The program pauses and turns on that light to show waiting for input. The user can toggle any of these lights and hit that button to confirm. It sets the main memory register and resumes the program. Over here is the proof of concept for a proper addressable memory bank, though currently it only holds 16 bytes, using 4 bits from the secondary register as an address. Expanding it to 256 bytes should be doable, but it would be slow and take up a lot of space, and all my existing programs can manage with the loop of memory here. This loop of 33 bytes can move left or right one at a time, replacing the main register as it goes. It's very effective and space efficient, and moving a fixed amount is quick, but any indexing requires loops, which brings us to the largest issue with this particular architecture. Similar to the BF-based computer I built previously, there is no space for arguments in these 5-bit instructions. Each instruction is represented by a single character in the program. If I want to branch in any way, either to return to the start of a loop or skip over some code, I can't include a destination in the assembled code. To skip code, the start loop instruction will check if the register is 0, and if so, it will jump to the matching end loop instruction. The end loop instruction will do the opposite. If it is reached and the register is non-zero, it will rewind the code to the matching start loop. In these circuits, this must be done 1 instruction at a time at clock speed. These gates prevent the instructions from reaching the circuits and being run, and these droppers count loop brackets until the matching one is reached. Any loop or if state in a program is thus very slow, including things like seeking for specific memory in the array, or returning to the start of a turn for a game. This is another thing that could be addressed by large addressable memory, but the difference in memory speed and capacity is significant. Bit of a trade-off, depending on purpose, really. Sneaking into the timing circuits here, the last instructions to mention are this one to skip the next instruction if the current register is non-zero, and this one to fully end the program. For example programs, I have a complete list. I've already selected a creeper face, so we can start the program running. It does take quite a while, but the individual operations are quick themselves. The program is read from this disk here. Right next to that, this counter tracks which disk to read from, using these gravel gates to let the signal through. From there, it turns a few corners and goes through a few more gates before traveling along this main bus to activate all the different instructions. The output from those instructions then gets passed to all of the instructions and copper bulbs along the main bus here. And we can see all of them updating in sync. The byte of memory on the left shows which column is currently selected by the mask, and the main register is then used to select the rows that will be updated. And that is the end of the program. You can also see the various values calculated in the main array. For other static examples, I've got a program to generate a Sierpinski triangle, so we can run that one now. Press this button to full clear the screen, cycling through all of the different screen states. And start program here. This one takes a little bit to set up, and then we'll accept an input right here. It then uses that input as its starting state for the first line. Afterward, it will use a bunch of math to calculate the following lines as a cellular automata, a one-dimensional cellular automata. However, as stated before, when it reaches the end of each line, it has to disable operation and loop the program slowly back to the beginning. It then resumes forward and gets to work calculating the next line. Glancing through these circuits, we can again see plenty of the experiments I made while designing the computer, the different designs for arrays. This ended up being the main memory loop. These are all the experiments on the best capacity and speed for the program storage. I did want to make sure that both loops would be read with the exact same timing. Over here, we also have experiments on getting the screen and being able to reset it, as well as experiments for larger screens with readable memory. And at this point, we will take advantage of newer features of Minecraft to sprint through the last two lines. Rule 30 is a similar program, a similar one-dimensional automata that runs from the top down. And honestly, I can skip running it. Now, for the more impressive and more complicated programs, we can go to Connect 4. And I can just get it started. In the back over there, we can see the array of finished programs that my buttons there are using command blocks to swap out. Debugging, resetting memory, and swapping out the programs are the only things that I use command blocks for. I had an intention to make a physical circuit to rewind the program to the beginning, but never did. But yeah. Over here, we've got 4 disks for each program. And I do have Python code both to test the programs before writing them into the game, as well as a program to display what the copper bulbs should be set to make it as easy as possible to write out these programs just by manually using a redstone block on these bulbs. All of my programs are written to assume that the memory may be in an undefined situation. And so programs like Connect 4 begin with a loop to clear memory and get things set up for the game. Connect 4 is thus written that you just select which column you want to drop a piece into and hit the confirm button. This still does take a long time, but it is interesting to watch. As we watch here, it will take that input value and lower it and bit shift it lower down in each row in order to find the selected row. Again, when it does this, it needs to loop back to the beginning of the code to go to the next iteration. And here it has found the location. It will raise it up to indicate where the next space should be dropped. And then it uses a different loop to go back to the line here and locate that. This program also keeps a counter of turns. Since I was not able to fit wind detection into this program, I do have wind detection written for the tic-tac-toe program, but that does not fit into the amount of code this structure allows. Theoretically, I have designed things so another 4 disks of memory, of code memory, could be set over here, but I think I would have to adjust a lot of this timing, which would be a chore. I would have to shove it into a smaller space. Therefore, without wind detection, the program ends either if you enter a 0 in as input, or when this turn counter runs out, which shows when the board will be filled completely. These lights here keep track of which disk is currently selected. So as we rewind, that lamp will loop around the program a few times. Oh. The lamp has gone around the program a few times. So just for demonstration, the other player, which is indicated by this lamp's being off. First player shows the lamps being on. Just for demonstration, the second player will play above the first. Now to skip, I believe 300-ish seconds is about right. Again, the computer does run at 1.25 hertz with 8 ticks in the main clock. However, the limited size, the limited instructions, and the size of the programs does limit speed, does make the programs take quite a lot longer. But as you can see here, the first player is designated by the 2 unexposed copper bulbs being lit up, and the second player is indicated by the exposed copper bulbs lighting up. The first player can then select another row, and the cycle continues. Hopefully that is enough of a demonstration for this particular program. Resetting the input, so I don't have to worry about that. And moving to the next program, I will clear the screen. And again, the other programs assume messy, uninitialized memory, so it should be fine to just go straight to the tic-tac board. Even without wind detection, the tic-tac-toe board, the tic-tac-toe game takes a lot of code, so I had to split this up into 2 programs. One to run to set up the board and most of the memory, and a second that is just the game loop. Here it is taking advantage of the mask structure and being able to update entire rows of the screen at once. And that is the end of the tic-tac board program. Moving on to the game and letting it set up. It'll take a little bit to set up, which is actually the start of turn or end of previous turn kind of setup. Now that it is ready for input, I have included a guide for basic instructions, including the tic-tac-toe board. Recently, I have realized better ways to arrange this input, but given 8 bits of input and 9 bits and 9 different spaces to go in, and this was the one I put together at the time. So starting in the middle, I'll go 1, 2, 3, 4, 5. Leftmost bit is lowest 1, so is and lowest to highest on the registers as well. Certain areas of the computer have a lot of sound, especially when sprinting through. As you can see, this has played in the middle for the first player. Second player, I'll go bottom right for a full demonstration. All right, that should be the second player's turn. Top middle. Well, that should be a good view of the project. I technically started working on it almost 2 years ago, beginning of 2024, but I am not good with sticking to one project for a long time, and it has been an on and off procrastination project for most of that. I want to say 3 or 4 months of active effort, but I have no way to measure that. Technically, I got the first two cellular automata programmings working like a year ago, but then was not really looking forward to debugging the longer ones. But now that all of it is done, I am Stewin, and thanks for watching.